Okay, so this is a video on rank, nullity, and systems. The very first thing that we have here is what we're going to call the rank and nullity theorem. Okay, so the way this thing works is that if I have an M by N matrix, so this thing does not have to be square. And I know that the rank of that matrix is R. Then I also know that the nullity of that matrix, so we're just going to make that nullity of that matrix is N minus R. So it's the number of columns minus its rank. Another way of saying this is to say that the rank of the matrix plus the nullity of the matrix has to equal the number of the columns. Okay, so there is an implication here that the nullity is the number of, quote, free variables that would solve the linear system that is involved with A. So if I have A times X is equal to B, then the number of free variables or parameters that I would need to describe the solution is equal to the nullity. So let's put this to an example. All right, so let's let A be a 4 by 5 matrix. So we have 1, -1, 2, 3, 1, 2, -1, 1, 2, 1, 3, 0, -2, 1, 2, -1, -2, 6, 5, 0. If you did Gauss-Jordan on this, you're going to get 1, 0, 0, 3, 2, 0, 1, 0, 8, 5, 0, 0, 1, 4, 2, 0, 0, 0, 0, 0. Okay, so this implies, so if I look here, I've got this 3 by 3 identity going on there, so that tells me that the rank of A is 3. This means that the nullity of A has to be 5 minus 3 or 2, which is these last two columns. Now if you think about this, this gives me two free variables, right? x5 and x4. I can make that s and t. That implies that x3 should be -2s minus 4t. x2 should be -5s minus 8t, and x1 should be -2s minus 3t, which means that if I had the homogeneous system of equations, then the solution would have to be t times the vector -3, -8, -4, 1, 0, plus s times the vector -2, -5, -2, 0, 1. So the linear combination of these two vectors is going to be the solutions, the set of all solutions for the homogeneous equation. So let's kind of pull this together a bit, because what's going to happen here is we're going to get a theorem that allows us to relate this reality to not only the set of homogeneous solutions, but the set of non-homogeneous equations. So the solutions to the set of the solutions to the system of non-homogeneous equations. The set of solutions to the non-homogeneous system of equations. All right, so let's take a look at that. Okay, so we're going to get a quick theorem here. This theorem says that if xp solves the non-homogeneous system of equations, okay, so it's a particular solution, right? Then every solution, so then every x that solves ax equals b can be written as x equals xh plus xp, where the xh vector is a solution to the homogeneous system. So the idea here is that if I have one solution, just any given solution to this system, then if I add that solution to a solution to the homogeneous system, I get another solution to this. So if I have all the homogeneous solutions and any particular solution, then I have all the solutions to the non-homogeneous system of equations. So proving this is actually kind of simple. Take A and have it work on the difference of the particular solution and some arbitrary solution. Okay, so this works out to be that by left-hand distribution, right? But each of these, because this is an arbitrary solution to the homogeneous or non-homogeneous system, and this is a particular solution, both solve the system, so they're both going to resolve to the b vector, which when you subtract that, you get the 0 vector, which means that this is a solution to the homogeneous system, which means this has to equal sum h, okay? And then just a little bit of quick algebra, and this has to be xh plus xp, which is what we're trying to prove. So every single arbitrary solution to this system has to be a solution to the homogeneous system plus that particular solution that I found with. So let's see what this looks like in practice. All right, so let's say A is a 3x4 matrix. And B is some vector 5, 8, negative 9, right? Then I am going to let x equal b, and I want to solve for x. And I can do this using Gauss-Jordan, right? 1, 0, negative 2, 1, 5, 3, 1, negative 5, 0, 8, 1, 2, 0, negative 5, 9, right? And we apply Gauss-Jordan to this, and we would end up with 1, 0, -2, 1, 5, 0, 1, 1, -3, -7, 0, 0, 0, 0, 0. Okay, so this means that let's let xp be the vector 5, -7, 0, 0. That's a particular solution. If I put this solution in, that's just the solution that if I make s and t equal to 0 is going to give me back -9, right? Let's make that a -9, not just a 9, right? We got that. All right, so now, what if I were to make this the homogeneous case? So what does that look like? Well, this here would just be zeros. And then this here, because of the way that Gauss-Jordan works, is also going to be working out to be zeros. So that's my homogeneous case. Well, the solutions to the homogeneous are infinite here. I have 4 variables in play, so let x4 be s, let x3 be t, right? So x2 is, what do I got there? 3s minus t. x1 comes out as s plus -s plus 2t, right? So this means that xh is going to be of the form s times -1301 plus some t times the form 2 -110, right? So this means that every single solution to the non-homogeneous case can be written as x is equal to this one of these xh's plus this particular solution. And now I have the set of all possible all possible solutions to the non-homogeneous equation. So I just take the homogeneous solution and I add this to the end of it. So it would be s times this plus t times this plus xp. So that gives me a quick way to find a set of solutions to the non-homogeneous system of equations. Okay, so there's a couple summary theorems here that catch some details of things that we've been working on. Okay, so one theorem is about the number of solutions. So if I have a non-homogeneous system of equations, if the rank of A is n, okay, so if this is a full rank, then I have a unique solution. Okay, number 2, if the rank of A is equal to the rank of A when augmented with B, okay, and that's less than n, then I have an infinite number of solutions. So my system of equations is underdetermined. I have an infinite number of solutions. If the rank of A is less than the rank of the augment, then I have an overdetermined system of equations and there are no solutions. Okay, so that's part of the trick there. So this is something like you could use to make a determination about your set of solutions before actually finding the specific values. Like, there's no point in trying to describe the solution set if there are in fact no solutions. So this is an existence and uniqueness theorem, right? So this tells me whether or not there is existence, and this tells me whether there is uniqueness. Okay, so the other summary theorem I want to do is go back to that idea of equivalent statements of square matrices, because we have more now. Okay, so let's say that A is a square matrix, n by n. Then the following statements are equivalent. Okay, following statements are equivalent. 1, A is invertible. Okay, so it's non-singular, it's invertible. AX is equal to B, has a unique solution. 3, the homogeneous case has only the trivial solution, which is the appropriate zero vector, right? Number 4, A has to be row equivalent to the identity. So I can use a set of elementary row operations and get the identity. The determinant of A cannot be 0. The rank of A has to be n, so it has to be full rank. Number 7, the row vectors of A are linearly independent. And 8, the column vectors of A are also linearly independent. Okay, so these 8 things, if you have a square matrix, all say the same thing. Okay, so they can be interchanged for one another. All right, so there's our bit on rank, nullity, and the solutions of systems of homogeneous and non-homogeneous equations.